Okay, welcome everyone to this seminar. Let's just give it a moment or two to allow people to join while I give a brief introduction. So this is part of our seminar series looking at decarbonisation of heating. Today we have two excellent speakers who are going to talk about the use of thermal energy storage solutions. We will have time at the end for some questions, and so if you do have questions, please type them into the chat and we can put them to our speakers at the end. Okay, next slide, please. So just in terms of housekeeping, this event will be recorded. The questions that you type in, I will read out, so you won't necessarily be recorded, but the responses of the speakers will be recorded. We've disabled all other media to allow for smoother presentations. And as I said, if you can submit any questions through the Q&A and chat, if you do it throughout the presentation, I will come to them at the end. Slides may be available at speaker's discretion and confirmed later. So these can be available if you ask for them. So next slide, please. So really, I think it's just for me to introduce our speakers. So our first speaker is Kevin Rushbrook from Spirax Group. He's going to give us, as you see here, a review of commercial readiness of some of the technologies that are out there and that people are talking about. So over to you, Kevin.
Thank you. Hello, everyone. So quick introduction before I start the presentation. My name is Kevin Rushbrook, as Stuart says. So my role is technology analyst for Spirax Group. So I look at emerging technologies and how they're relevant to our steam business, which consists of Gestra and Spirax Sarco. So what we're going to be looking at today is technology and commercial readiness level of industrial steam generation thermal energy storage systems. So this analysis aims to identify which technologies are most ready for commercial adoption. So the benchmark level for inclusion in this analysis is a technology has reached a TRL level of 6 or higher. So for those of you familiar with TRL levels, that one means that the technology has been demonstrated in a relevant environment. And within Spirax, we define that as a fully working system has been shown to operate across the full performance envelope in an environment that represents the final operating environment. So typically in a test facility or on a customer site. And for industrial steam applications, we mean systems capable of generating 10 bar gauge saturated steam. So that is the equivalent of about 185 degrees C, and we estimate that covers about 80% of industrial steam applications that are relevant to us. That includes food and beverage industry, where the steam is used for cooking, distillation, pasteurization, pharmaceutical industry, where it's also used for drying and sterilization, in hospitals, and in pulp and paper industry, where it's used for digesters, drying, in corrugating machines, and also for gluing pulp and paper. Out of scope of this analysis are domestic scale energy storage solutions or utility scale thermal energy storage solutions. And before I get into the details, I'll caveat that with this is primarily secondary research, so the analysis is highly dependent on the quality of information that's available in the public domain. So moving on, a quick introduction to why we use thermal energy storage in industrial applications. And there's two main sets of benefits. The most obvious ones are the downstream benefits for the people using the steam or the energy. And the first one of those is decoupling supply and demand. So demand shifting enables local storage of the energy for later use. And that's most valuable where you want to use, say, off-peak electricity, so you can store it overnight and use it during the day, or where you have intermittent renewables. Another benefit of thermal energy storage is peak load reduction. So one of the challenges with electrification is that steam boilers and other heat loads can have very high peak demands. So using thermal energy storage allows you to spread out that demand over the day and still meet your supply demand. And the next one is process optimization. So this one is more about reusing energy flows within the process. So that's the downstream benefits. The benefits that maybe aren't so obvious to the people looking at the process plants are the upstream benefits. So thermal energy storage can allow you to improve how you manage your energy supply network. So you can do load balancing on the grid, say, and there's companies that have started actually selling grid balancing as a service by providing thermal energy storage solutions. The next one is variable supply integration. So it's sort of related to the downstream benefits in that it allows easier integration of renewables, such as wind and solar. So I see there's somebody got their hand up for a question. I think we're going to take questions at the end, if that's all right. So moving on.
I've just put a reminder in the chat, people, please use Q&A or the chat rather than put your hands up. Maybe we can talk at the end. It depends how the time goes.
Thanks.
Oh, and while I'm there, Kevin, your camera's not on, so maybe you want to just show your face.
There you go. Hi, everyone. Okay, so I've described why we use thermal energy storage. I also wanted to cover why we still use steam as a heat transfer fluid rather than some other alternatives. So for those of you who've used steam, you know it has some quite unique benefits in the process industry. So the first one is has a very high heat content, of which a very large proportion is contained in the latent heat. And that latent heat can be released very quickly and probably most importantly at a constant temperature. So that allows very easy control of temperature just by using pressure control. It's self-distributing, so because it's an elastic fluid, large amounts of steam can be driven through a process and through pipework very quickly without really needing pumps to be distributed around the system. It's safe and sustainable, so water is non-toxic, it's non-flammable, and in most countries, it's fairly readily available. And it's also easy to control, so steam is essentially self-regulating, and usually only pressure control is needed. So that's a recap of why steam is a very useful heat transfer fluid in process industries and other applications. So moving on, we'll be describing three main thermal energy storage methods in the later analysis. So the first one is sensible heat storage. So that's where you store heat by raising the temperature of a solid or a liquid material without changing the phase. So the phase of your storage media doesn't change. We'll separately look at solid and liquid as two separate categories. The next category we'll look at is latent heat storage. So this is where you use a phase transition in the storage media to capture and release thermal energy. So during the phase change where you're changing from one phase to the other, energy is added or removed from the material, again at a constant temperature. In practice, most latent heat storage solutions you'll see out there in the market also have a bit of sensible heat storage as well. So you will heat the media up to a certain point where you'll get a phase transition, and then you might also heat it beyond that phase transition temperature again. And the last storage method we'll look at are thermochemical storage systems. So they use a reversal chemical reaction such as hot salt hydration to store energy. So looking at the first of those in more detail, so solid state sensible heat storage. So again, this is where we store heat by raising the temperature of a solid material, but without changing its phase. So the material remains in the solid phase all the way through the heating and cooling process. There are two main groups of products on the market that we've looked for in this analysis. The first group I've called high temperature systems. So those typically use a storage temperature of 400 to about 750 degrees C, and they use fairly readily available materials such as concrete or rock as a storage media. Because those media have fairly low thermal conductivity, they often include them in a metal matrix to include your energy output rate. And solutions that are available on the market frequently include pipework through the matrix for energy extraction. So you will flow air or water or another media through your storage media in pipework. And most offerings within this group, we'll see later, they're modularized. So they'll have one or two standard sizes that they mass produce to reduce costs, and then you will scale up or out by adding units in series or parallel to meet your required energy or power ratings. The next group of solutions I'm going to look at under solid state sensible heat storage are what I've called extreme temperature systems. So they operate at above 1,000 degrees C, and they use more specialist materials such as refractory materials, graphite or silicon. So the mass production side there usually comes in just they use standard size bricks, and because of the high temperatures, air flow around the stack is usually used as a heat transfer fluid. Though there are some people using infrared radiation as the proposed output method there in the early stages of development. But in this case, extreme temperature systems tend to be bespoke builds. So each system will be designed and built specifically to a customer requirement. So looking at the commercial readiness of solid state systems. So of the systems I'm going to be looking at, solid state TES is the most commercially mature system for industrial steam generation. There are many companies, over 13 that we've identified, having declared successful technology demonstrators or have pilot sites that they've have in operation. There's at least 2 companies, I think is more now, probably about 4, with ongoing commercial operations. So that's where they've advanced beyond just having a technology demonstrator. They actually have sales of established products on a repeat basis. And there's at least 2 companies developing what they call gigafactories. So they've invested tens of millions of dollars plus on a factory facility where they're producing over 2 gigawatt hours of storage capacity per annum. So for a typically sized storage module, you're talking about the ability to produce thousands of modules a year. So we can see there's at least 2 companies are very high on the commercial readiness level. So moving on to liquid state sensible heat storage. This is where you store heat by raising the temperature of a liquid again without changing its phase. So we already know that things like hot water tanks and steam accumulators are very well known and pretty much ubiquitous, but they offer limited opportunities for steam decarbonisation due to the lower storage temperatures. So for this analysis, we're looking at 2 technologies available that enable steam generation to be decarbonised in terms of liquid state sensible heat storage. The first one is high pressure water storage. So this operates on a very similar method to a steam accumulator in that you're storing water at very high pressure, then you're releasing the pressure to generate steam when you want it. But the energy you're using is the sensible heat stored in the hot water. They differ from steam accumulators mainly in how you add energy to the system. So you would use electric heaters or similar to add energy, and that's much more efficient than condensing steam. The second system we're going to look at in terms of liquid state sensible heat storage are molten salt systems. So these are systems that use molten salt that you store at one temperature, and then you heat that up and store it another. Usually they use separate tanks, so they have a cold tank and a hot tank, and you will pump salt out of a cold tank, heat it up and put it into the hot tank. Obviously we're talking about molten salts here, so cold tank temperatures are relative. They still need to be about 200, 300 degrees C, even from cold. So their ability to have a high temperature lift and store a lot of energy can be less than some other technologies, just because your temperature difference from cold to hot can have limited. One benefit of those is that you can separate your heat exchanger from storage, so you can scale the power and the energy entirely as required per site basis. And moving on to latent heat storage. So this is where you use a phase transition in the storage media to capture and release thermal energy. So during the phase change, energy is added or removed from the material at a constant temperature, which makes this technology really suitable for temperature regulation applications. And that's where most commercial phase change materials are designed for. So they're designed for chilling or HVAC applications with temperature transition temperatures well below steam temperatures. So typically they'd be designed for refrigeration applications, so below zero, or human comfort temperatures, so around 20 to 30 degrees. So those organic phase change materials aren't yet really suitable for steam generation, but there are a small number of commercial solutions using latent heat storage at steam relevant temperatures, and many of those use aluminium alloys with a melting point of around 500 to 700 degrees C, either in bulk or encapsulated within a storage material such as the sort of graphite materials we talked about previously. Another example of those is a silicon-based eutectic with a melting temperature of 14 degrees C, which led to the name of the company that's actually selling those. And the last technique I'm going to describe is thermochemical storage. So that technology is based on the use of reversible chemical reactions or absorption-desorption process. So there's been a lot of academic output in this area, but very limited industrial application of the technology. So from the information we've been able to find, there's only one company actually selling a thermochemical storage system called Saltex, and that uses hydrated salt as their storage method. So that was a very quick summary of the different techniques that are available commercially for thermal energy storage for steam generation. So the next slide is a comparison of the different operation ranges that the different technologies that we've just described can give. So you'll see here sort of high pressure hot water systems are coloured in blue, latent heat thermal energy storage systems in orange, liquid solid state in grey, and solid state in yellow. So you can see most of them operate within a band. Sorry, in the x-axis is energy, and in the y-axis we have power, both of them logarithmic. So most systems operate within a band where the ratio of power to energy is fairly constant. There's a slight difference between the different technologies. So liquid latent heat storage has a much higher power to energy ratio than the others. So that means it may be particularly good for solutions where you need relatively peaky power demand over the course of the day. And the others are relatively within the same band. And if you look at the ranges that each of those technologies can cover, so on the x-axis here, we're looking at that power to energy ratio. So towards the left, you've got systems that are probably better for longer term storage because they store a lot of energy in relation to the power output rate they can produce. On the right, you've got systems that are probably more applicable to either short-term storage or where you need to meet very high instantaneous peak demands. And on the left, y-axis, you have the storage temperatures available. So you can see that solid state storage systems that use latent heat can cover quite a broad range of storage temperatures and also power to energy ratios. Latent heat storage are somewhere in the middle. Molten salt, the temperatures you can get to aren't as high, but you can tailor probably the power to energy ratio. That's a result of really being able to separate your storage from your heat extraction techniques. And there you can see sort of high pressure hot water is probably filling a different part of the requirement spectrum. So it has a higher power to energy ratio than some of the other technologies, but it operates at a lower storage temperature. So maybe can't get up to the higher steam pressures that some of the other systems can. So summarizing and comparing the different technologies. So the section on the left of the slide is technology readiness level for each of the technologies. The band is the technology readiness level of the different products we could identify. And you'll see there that solid state technology, as we mentioned earlier, is by far the most sort of commercially ready technology at the moment. Higher temperature solid state is still not as mature, so there are pilot sites out there, but no commercial adoption as yet. The only other technology that's met sort of commercial adoption is the molten salt systems. Then you'll see that sort of high pressure hot water, molten metals, and salt hydration in terms of thermochemical are still not as mature yet. They're still around TRL 7. So they're not really commercially mature yet. In terms of level of activity, so this is the number of different companies we've identified that are actually developing products in this using these technologies. Solid state is by far the most popular area, so there are many companies using that technology. There are quite a few companies looking at high temperature solid state and using latent heat storage. So probably about 5 to 10 companies using those technologies. There are much fewer companies looking at high pressure hot water, at molten salt, or at salt hydration. So less than 5 companies for each of those areas. And I won't run through this slide in detail, but the other information on here is energy density. So you can see that salt hydration has the potential to store much more energy in terms of kilojoules per kilogram, but it would be it's also a much more expensive storage method as well. Solid state is probably by far the cheapest material aside from hot water. But again, you need to look at other factors such as power density and overall system cost. So very quick summary from me. So no technology, we believe, has yet reached very widespread commercial adoption. Solid state thermal energy storage is by far the most commercially mature and has the broadest operating range. High pressure hot water and molten salt are closer in temperature range to the ranges required for industrial steam, but are less mature at the moment. High pressure hot water may be more applicable for applications which demand high instantaneous power. And liquid sensible heat storage can be more flexible due to the ease of separation of storage and heat transfer functions. So I hope you found that useful. I'm aware there probably wasn't as much technical detail in there as you might have wanted, but the purpose of this analysis really was looking at commercial and technology readiness levels. And hopefully we provided that. Thank you.
Okay, thank you, Kevin. So we'll save questions to the end. So our second speaker will hopefully share his slides just while we change over. So we'll save questions to the end. So I would like to welcome Daniel Wells, who also works for Spirex, and he's going to tell us about the use of steam. So over to you, Daniel.
Great, thank you very much for that introduction, Stuart, and thanks also to Kevin for a very interesting and insightful overview of the commercial readiness of different thermal energy storage solutions that we're currently aware of in the market. And I think it's fair to say that Spirax-Sarco, our expertise is principally in steam and steam generation. So our experience to date is essentially with the high pressure hot water storage solutions, and also through a recent investment in a company called Kyoto that manufacture those molten salt storage solutions that Kevin referenced. I think one thing that it's important to understand is if we are going to make that transition from a traditional source of energy, I'm going to use natural gas as an example, towards a thermal energy storage solution, there are steps that we need to consider. We need to ensure that we're making the correct decision for all the correct reasons. And again, we keep harking back to steam. And we appreciate that there are many different sources of energy, but our experience is in steam systems. Steam is very much the preferred source of energy for the vast majority of industrial applications for just some of the reasons we can see on the screen. Over towards the left-hand side of the screen, it reminds us that there's a very, very high energy density with steam. For example, if we compare a kilogram of steam to a kilogram of water, when that water's circulated across a heat exchanger, the only way it can give up its energy is by cooling down by a certain number of degrees. Whereas steam's got a much greater energy content, and at the same time, when it gives up its heat energy, it condenses. But when it condenses, it doesn't actually cool down. So it reminds us, if we're able to reuse the energy in the condensate, there is some value there. We also know that if we can use steam as a compressible media compared to water, we know that the infrastructure is going to be considerably smaller. And as Kevin mentioned in his presentation, as an elastic media, we don't have to pump steam. It's going to move in accordance with the pressure drop. Now, if we compare a traditional steam system that is fired by natural gas, because there's considerably more energy that's available in natural gas compared to electricity, it means that a traditional gas-fired steam boiler can respond very, very quickly to accurately, reliably, efficiently meet those huge instantaneous peak demands that there may be. And that's something that a similarly sized heat pump or an electrically operated steam boiler are really, really going to struggle to achieve. So it really reminds us of the place that energy storage has for the vast majority of industrial applications. But of course, it's attractive to look at these new innovations and move towards them as a knee-jerk reaction to really decarbonize our thermal energy demand. But it's completely the wrong thing to do that without due consideration and process. The simple reason is, if we look at a traditional, it doesn't have to be steam, if we look at a traditional process that's using a significant amount of thermal energy, then we appreciate that there is going to be a significant number of inefficiencies at different stages between the point of generation and the point of use. It's inevitable. That process may have been designed and engineered 30 years ago when the cost of gas was low. So we lived with the inefficiencies because the cost of modifying the process or the infrastructure to iron out those inefficiencies, they may not have provided the payback that we expected. And 30, 40 years ago, we weren't as environmentally aware. So the carbon emissions were an afterthought. So the first step that we need to take is really to look at our existing process. For example, and I keep harking back to steam, but as an example, our steam generation in the energy centre could be 10,000 kilograms per hour, when in actual fact, our process may only require 7,000 kilograms per hour. So understanding where those inefficiencies are means that that boiler doesn't have to work as hard. So I keep harking back to this point. It's really critical at the very, very outset that we fully understand our process profile. We need to understand not just how much steam we require on a daily or hourly basis. We need to break that down on a granular, on an asset level, minute by minute, or 15-minute intervals, for example. By understanding our load profile, it's going to help us to understand the appropriate thermal energy storage solution that we then need to engineer. And of course, once we've fully optimized and understood our steam generation, the next thing we really need to think about is putting in place a robust scheme to manage that process. We need to make sure that those inefficiencies aren't going to creep back in over time. So on the optimized stage, using a traditional gas-fired steam boiler, we know where those inefficiencies are likely to exist with a traditional steam system. So you can see that there are a number of different losses, for example, the flue losses, the radiation losses, that we're simply going to have to learn to live with, for example. Sure, we might be able to put an economizer on the flue to minimize those losses, but we're never going to be able to completely eradicate them. All we can really do is put in place a regime to either reduce those losses or to recover some of that heat energy in some way, perhaps even putting that waste heat stream back into some thermal solution storage. The next step, as I've mentioned, it's managing. It's some means of not just manual intervention to provide routine energy audits and surveys and so forth, but it's moving towards digitalization. If we can embrace a means to continuously manage and understand not just our efficiency, but our load profiles, then perhaps we can modify the process in some way, change the process, change the shift patterns to something that's more palatable and more aligned to any future thermal energy storage solution that we might be then able to engineer. And that then brings us on to the third stage, the innovations that Kevin's spoken about. We should only really consider those innovations when we've taken steps to both optimize and manage our existing thermal energy system. And that probably starts off with something simple like putting in place the appropriate number of steam meters. If we've got the appropriate number of steam or thermal energy meters on our point of generation, on our distribution system, and our point of use, we can understand where those inefficiencies are, and we can start to understand how we use the steam. For example, if we're looking at the load profile on the screen, we can understand where those peaks in demand really are. And once we know where those peaks in demand are, we can decide what the appropriate solution is likely to be. And in many cases, it may well be that one of those high pressure hot water storage solutions may be able to provide a significant mass of steam to satisfy the demand for those peaks instantaneously and efficiently. And we may determine that we need some other solution, for example, an electric steam boiler, in order to provide the remaining energy that is required by the process. So I think the short answer is that there's no single solution. There is no magic bullet that can satisfy the thermal energy demands of every process. It's highly likely that if we're going to move towards decarbonised steam in the future, we're going to have to adopt a mix of technologies. But it's critically important that we take that three-step approach. We first optimize our existing system to iron out the existing and inherent inefficiencies, and then move towards some form of digitalization, not just so that we understand where the inefficiencies may be, so that we can act on them, but also that we can fully understand how much thermal energy we need and when, so that we can then engineer the appropriate solution in order to provide that decarbonised thermal energy. So I'd like to thank you very much for your time for listening and attending to this this afternoon's webinar, and pass you back to Stuart, the chair.
Okay, thank you, Daniel. That was excellent. So just to finish off, we'll have time for questions in a moment. You can see on the screen that we have a YouTube channel where we can access recordings from these seminars. So hopefully this particular seminar will be available on there very shortly. So I'd encourage you to have a look at those. Next slide, please. There's also a upcoming talk on the 12th of November, which obviously people are welcome to attend, looking at the reality of living in a world where the temperatures have risen, so looking at resilience. Next slide. Okay, and finally, just to finish off and before we get into questions, should you like a CPD certificate, you can contact me at Islam. The website is on the screen. There's also feedback for the event, should you wish to give feedback and let us know what you thought of the talks or the seminar series. This talk is done in with the Process Industries division, which has its own section on the IMechE website, so I encourage people to have a look there. So that's it for housekeeping. I think it's now time to look at the questions. So let me open up the chat window and the question and answer window. So if people do have questions, and I saw someone had put a hand up, please do type them out into the chat window and the Q&A, and I will put them to our speakers.
Please, can the other speakers pop the cameras on as well, so we can see them both, or even if anybody else is joining in on the panel.
I can see Daniel. I can see Kevin. Richard, would you like to join us on the panel?
It sounds like I will.
Excellent, thank you. It was a slightly loaded invite there, wasn't it?
It was, and I didn't expect to be in this, so that's why I'm in my t-shirt and my cardi, but there you go, dressed to impress.
Okay, well, I mean, I'm going to take the sort of chair's privilege and just ask the first question, if I may, just while we warm up and give people time to. So I noticed that the benefit of something like a steam boiler, in one sense, is it's not really doing energy storage; it's doing load leveling. It allows you to install a much smaller boiler for the peak to meet peak loads. And I wondered where the benefits were compared to just savings in capital cost, and how that translates to systems that are used for carbon savings, and where the interaction is. Daniel, do you have any thoughts on that?
It's a good question, and I don't think that there's any easy answer, for the simple reason that every process, whether it's steam using or any other means of thermal energy, is going to be unique. My personal thoughts are, with an electric steam boiler, it's definitely got its place. Certainly for masses of steam that are required with a relatively low base. I'm talking up to a maximum of 5,000 kilograms per hour. Beyond that, then it's likely to be beyond the reach of the vast majority of sites existing electrical infrastructure. And that really is when an alternative means of thermal energy storage is really going to be beneficial there, in order to supplement the any instantaneous peak demand for energy that there may be.
So in one sense, it's very much the storage is very much an enabling technology for the electric boiler. It allows it to work. I mean, I just wondered about thoughts on, in terms of harvesting of renewable power. So obviously these systems are being powered by electricity. Do you envisage a time when this is effectively going to be load following, based on the carbon intensity of the grid?
I think there's a potential for that, for definite. Whether or not there's technological readiness at this stage, I don't know. Perhaps Kevin's got an opinion on that.
So, yeah, so there's already companies out there that are doing heat as a service, where they will have a thermal energy storage plant next to the customer, where they will essentially sell the steam to the customer, and they promise that steam will be available as and when it's needed. But they are also selling load balancing services to the grid, so they're only pulling electricity off the grid sort of when it's cheapest, or they will stop pulling electricity when the grid needs to balance the overall grid load. So it's already happening. It's probably not very widespread, and there's only a couple of people doing it, but it is starting to happen.
Richard, any thoughts?
I've got loads of thoughts. I've got some questions though, because the problem is it's not quite blue sky, but we're not totally immature. So it would have been lovely to see pictures of tanks and storage systems being used by people. And clearly we're not, even though it's relatively mature, we're not in a position where we can do that for confidentiality reasons or whatever else. But I'd just like to come back to the point that Daniel made as well about optimization. There's so many boiler plants, CHP plants, other energy solutions in the past that have been sized for a process. The economy's been hit. People have reduced the size of the process, reduced production. Suddenly they've got an oversized facility, or they've just made their plant more efficient and then suddenly it's still oversized. So you really got to go the extra mile to make sure that your generation is efficient, your distribution is efficient, you've got your condensate return if it's steam, that's 11%, 12% saving on energy straight away. Radiation losses in steam mains, traps, everything is right. And as well as that the end use processes have been optimized, because if you don't get that lot first, I suspect if we tried to size a thermal energy solution, it could just end up being a white elephant in a few years. Any thoughts about that? So anybody on the panel?
100%. It all comes back to understanding your process and making the right decision for the right reasons. We can't emphasize that enough. The last thing that we as an organization want to do is to encourage our clients to invest in what will ultimately be a white elephant. We need to optimize, manage, and only then should we with confidence engineer the appropriate solution.
So can I just follow up on that? Sorry if there's other questions coming in, but I think you didn't mention it, but I suspect this is only for 24/7 operations, really. Kevin, you're shaking your head.
No. So a lot of the case studies are for people that have normal 8-hour production cycles. So they might charge overnight when there's low rate electricity available.
Economy 7.
Yeah, exactly. And then use it during the day. And as I think Daniel said, one of the challenges with decarbonisation is there isn't really a single bullet. You almost need to look at every single sort of process plant individually and look at what are the energy flows and the energy resources available, and then look at what the best technologies are. It might be thermal energy storage, it might be heat pumps, it might be thermal solar or geothermal, or all sorts of other technologies. And it's like other decarbonisation technologies as well. You need to look at where you can make energy savings and improve efficiencies, as well as just looking at where you source the energy from.
And just my last question, because there's some questions in the chat as well. Energy pinch, heat sources and sinks. I would have thought when you're trying to optimize quite a complex system between generation of energy, use of energy, and minimizing the sizes, and then matching up the sources and the sinks, that energy pinch would be the way to go. I'm not an expert. I hadn't been mentioned. I just wondered.
Sorry, it's a phrase I'm not familiar with. So Daniel, do you know?
Yeah, 100%. They're things that we really need to look at as part of that optimization piece, Richard, to understand waste energy streams, to understand everything that we can possibly do to use one waste stream to supplement another. And thermal energy storage is an excellent heat sink in the vast majority of applications. Again, it comes down to understanding the process and what those waste energy streams are likely to be and when they're available and at what temperature profiles and so forth.
If people don't know about pinch, just look it up. But there's energy pinch, but there's also water and effluent pinch as well. And often instead of bolting on something big to deal with an effluent source or oversizing stuff, you can really reduce the size of the equipment you need. I'll shut up anyway because I'm monopolising it. Stuart, you're the chair.
Okay, well, thank you. No, it was great, good questions. I mean, we sort of covering some of the questions in discussion. I will read some of the questions out. So the first question was someone asking which optimization methods and decision variables are you using? I think, Daniel, when you're trying to decide what kind of technology fits, and Kevin Inner's thing. I guess what they're asking is, how do you decide which technology is optimal? What's the sort of key parameter you look for in a customer?
I'm going to speak with the Spirax Sarco head on again. I'm sure Kevin will be able to give a much broader opinion there. When it comes to looking at the thermal energy storage solution that may be applicable, my thoughts would be the mass of energy that is required, what the peaks are, but optimally what the recharge time is likely to be, what the recharge duration is likely to be. If we've got a 12-hour process, then there's likely to be sufficient recharge time for a thermal energy solution. If we've got a constant 24/7 process, then it's going to be a little bit more complex to engineer the appropriate solution.
Kevin, thoughts?
No, absolutely. So it's primarily about understanding your power and energy flows, and also other resources like water or materials, and modeling those if necessary. One thing that probably isn't done much is also scheduling your manufacturing process in accordance with energy availability rather than the other way around. It's probably something that could be done better. But yeah, not really adding much to what Daniel says.
I mean, I think what I'm hearing is what you're saying is that I can't just go buy an energy storage solution. That's not the way these things work. You really do have to sit down and do the whole exercise of energy optimization first, and to make it fit.
Absolutely. Yes, and really understand your process and what its energy requirements are and where you have flexibility.
So I suppose this leads on to a question, and maybe this is someone who works for Spirax and trying to get an advert in there, but it seems that it says, could you explain a bit more about what Spirax Sarco does and their key projects? I mean, I guess that sort of, you could talk a bit more about this. I mean, you don't just sell boilers, I guess, when you go to a customer's site, I suppose.
Yeah, I mean, this isn't the platform for a shameless promotion, but essentially, we do everything with thermal energy solutions. So everything steam, but most recently, it's also electric and renewable solutions to generate steam sustainably without a reliance on natural gas. If anyone does want any more information, please do reach out to me on LinkedIn, and I'm happy to give a slightly more salesy answer to that.
And I don't work for Sarco, but I've been using them for 40 years on and off, and boiler houses and all the products. And they run very useful training for people and some free webinars and seminars for customers and things. So in the UK, I'm not sure outside the UK, but good people you are.
What Richard said.
So to put it more in a sort of discussion context, and Jenny, you don't just sell equipment, and I think this would apply to all companies then working in your field, not just Spirax Sarco, that really in this field, the companies that operate have to sell a thermal energy management kind of system or solution, and which happens to include equipment.
Exactly, it's a solution. The products are just the tools that we have in the box, Stuart.
Yeah, and say that I think that must be true of all companies that operate in this space, because I mean the demands placed on them will be very similar.
It has to be. It has to be.
Okay, yeah. Just having a look at the chat. There aren't that many. Oh, so someone's. How could we estimate? So it's coming from. How could we estimate the benefit of boiler optimization? And I suppose that's a tricky question here, because you kind of hope the boilers are somewhat optimized, and you're talking about the benefits of changing to a different kind of system. So I don't know if you want to address those two issues: boiler optimization versus changing over to a new system and optimizing.
That's a topic in itself. We need to look at, first of all, is the boiler sized correctly? Is it insulated correctly? Have we got the correct boiler blowdown controls and level controls? Are they routinely serviced? Have we got the correct water chemistry? Have we got an economizer on the flue for a little bit of flue gas heat recovery? That there are so many parameters whereby just optimizing the boiler and the boiler controls alone, in many cases, that can see a significant gas reduction, which by nature means we're reducing the carbon emissions. So things that can be optimized with very little intrusivity to the boiler house, and with a proven financial payback. It really is one of the starting points, one of the first steps that we want to take whenever we're looking at reducing our existing demand and understanding what our true process requirement is.
Can I give an example? A boiler plant I had where we just did a simple infrared survey around the steam distribution. And I worked out that was 10,000 tons of steam a year we were losing because it wasn't lagged. It cost a payback was 6 weeks. If you don't do that stuff, and there's plenty of other examples, if you don't do that stuff, it won't work economically anyway.
Exactly, Richard. And that comes back to the point that if that plant was engineered 30, 40 years ago, that payback wouldn't have been attractive because of the cost of gas and the cost of steam versus the cost of infrastructure. It simply wouldn't have been attractive. We didn't know what carbon emissions were 30, 40 years ago. And if we did know, we didn't care. But today, we know that those efficiency savings, those optimizations, they're on the table.
There used to be, I mean, when I was doing these things, typically an energy project, most energy projects were paybacks of 4 to 6 years, and most companies won't touch them because if it's less, it's got to be less than a couple of years to even look at them. No one's asked the payback question, but you know, what have you any ideas of sort of payback on some of the schemes you've seen?
It depends upon the sophistication and how efficiently the existing plant is operating. You used the example of insulation, for example. A very, very quick win, and we wouldn't be at all surprised if an insulation system were to receive a payback, certainly within 12 months. But it depends upon how dry the steam is, what the losses are, the size of the pipework. Does the pipework run indoors or outdoors, for example? But yeah, it's highly feasible for us to look at certain optimization points around the loop that are providing a payback sub 12 months.
It's a bit of an analogy to air compression, similar sorts of approaches, but I won't get into that because it's the wrong webinar.
Absolutely, and an analogy we often use is we don't complain about our gas bill at home whilst we're leaving our bedroom window open and whilst we're leaving the hot tap running. The first thing we do is we make sure that we're being sensible about how we're using that gas. Before we make that complaint, and the same applies to our industrial system. We need to plug the leaks, and we need to act on those obvious inefficiencies as a starting point.
Good. Couple more questions coming in. Someone said that Kevin mentioned geothermal energy source. I don't. That's quite tricky because it's not really to do with storage, is it? So, and it's, you just take geothermal in here. I don't know if that's really relevant for this discussion. What do you think, Kevin?
So, yes, when I mentioned that was in context of the different decarbonisation technologies that are available. So, no, at the moment, we're not really seeing geothermal being used in combination with thermal energy storage, apart from very niche applications. It's more frequently started being talked about in combination with high temperature heat pumps. So you can use a low temperature geothermal source and then use a heat pump to boost that to temperatures that may allow you to generate steam that can then be distributed to a process.
Okay, that's good. Another question, and we're going a bit off topic here, but it's still very important. And the question is any of this technology likely to be scalable in a domestic setting? I mean, obviously, we're talking about process industries, but the other, a lot of the knowledge and a lot of the techniques must be the same. And I know for a fact that the companies that are selling, or purport to sell thermal energy storage solutions at the kind of scale for domestic heating system, building heating systems?
To a degree, domestic heating systems on a household basis tend to operate at much lower temperatures. Where one of the challenges with these steam generating temperatures is you need really good insulation, and that tends to be bulky. So when you scale it down, the insulation becomes much more volume. Where we are seeing sort of like not the really high temperatures, but intermediate temperatures being used is in district heating schemes and for sort of housing estate storage, where you might have centralized energy storage that will then get distributed to houses, also use the same sort of technology for hospitals. Bit of an aside, what's also interesting, and this isn't steam relevant at all, is people are starting to produce materials like plasterboards that have phase change material storage in them at human comfort temperature settings. So you can plaster your room with a board that will maintain the temperature at 23 degrees or whatever you want at. So it will store energy over the summer or during the day and then release that overnight to maintain room temperature. So some of the similar technologies are being used, but in a very different way.
Okay. I think what's interesting there is you said that there might actually be a direct analogy between process heating and district heating. So if we move, as the government is intending to move towards these heating networks, we're going to see the same kind of technologies and solutions that in the process industries being directly applied.
Yeah, I think the fluids that district heating systems use can vary quite a lot, and they tend to be quite different. Sorry, they can be different from process industries, but yes, a lot of the technologies and the products you would use are similar.
Okay, we're coming to end. I'll read one more question out. And I think this is what gets asked now in every question, in any session. And obviously, we've got to have a question about AI. It says, so any IA features applied to steam systems now? I mean, this, you mentioned, I think, Daniel, you mentioned digitization information. So there must be some impact on this new field on this.
Personally, I have no knowledge of that, but I wouldn't at all be surprised if my colleagues in our R&D division were already working on that. That wouldn't surprise me in the slightest. I think AI has got. I think it's got a place, because I think if AI is able to predict the process demand and the process requirement, and ultimately interpret that to some valuable information for the point of generation to understand what that load is likely to be in advance, I think that would be hugely valuable.
So what we're seeing is more use of tools like digital twins, where you can help understand what the process is doing digitally. And yes, you could apply use those models to help understand what changes to the system and how to better control it. Whether you call that AI is arguable. It's very different from something like a large language model, but it's still using a computer model to understand your system and how you can improve it. Things like scheduling as well, so doing production and energy scheduling, you could apply AI there, but to my mind, what we call AI is just another type of algorithm that you would be applying in that case.
Yes, of course, you're right. There's a big difference between, I think we would probably call it machine learning, the kind of digital twin, the better fitting and trying to extract information and make use of information. So yes, I can see the opportunities in that. I see lots of academic work on that. I don't work in the field, so I don't necessarily know how much is being applied in the wild energy systems. Okay, that's excellent. We're coming to the end of our hour. So thank you, first of all, to the speakers for two excellent talks. Thank you for Richard to joining the panel and also fixing the technical things as we went through. And also thank you to the audience and for your questions and for joining us. So and
Stuart, just pop up the last slide, will you, for the CPD slide, and we'll leave it up for a couple of minutes, and then I'll stop the recording. And just if people didn't manage to note the email address and the feedback form, if we leave that up for a couple of minutes, and say thank you to Stuart and to the speakers, Daniel and Kevin. Interesting discussions, and thanks for the quality of the questions as well.
Great, so thank you for the opportunity.
Quickly, will we be distributing slides to people who want them? I think that's a decision for Daniel and Kevin.
What we normally do with these is you've got Murat's email address there. If you want slides, either put it in the feedback form or ask Murat. But we're not about to issue 94 slide packs to everybody, just because we're all volunteers. We don't get paid for this stuff.
Okay, so I think the answer to the question someone's posted is if you email Murat, you can see his email on there. He may, if Kevin and Daniel are willing, provide the slides. We have to be a little bit careful with these things because sometimes the information, it's not necessarily confidential, but people want to keep control of information. Things like copyright and things can sometimes bite us. So.
And also in IMechE, we don't see your email addresses to people who are attending because of GDPR. We don't know how many people attended, but Murat does have those email addresses. I don't have those readily available. So yeah, your security is safe. And I think at that point, I think the slide's been up for a couple of minutes. Unless anybody's got any other things to add, thanks again, and I'll stop the recording.
Great. Thank you. Thank you all.
Thank you. Bye.
Bye.